just a circular loop carrying current. Okay? Now, what we want to do is solve for the magnetic field created by this current flowing around this loop. And by the way, this is very, very useful because you can model every atom as a current loop. Okay? And it produces a magnetic field that is similar to the magnetic field produced by a current loop. Just think about electrons spinning around the nucleus, think about the individual electrons spinning on their own axes. All of that produces a magnetic field. And it behaves kind of like the magnetic field we're talking about here. So, let's say that this is a current loop with a radius A, and this represents a small amount of the current loop that's shaped kind of like a macaroni noodle, and it's a current line segment. So this current line segment has an extent pointing out of the board like so, and I, D, ds. Current line segment IDS. And now this way we go to point P, and with radial vector R, which has a unit vector pointed along the same direction, little r hat. And notice if you take this all the way around the loop, everywhere the little unit vector r hat is perpendicular to the direction that the current element points, the current line element. So that's supposed to be, you know, the symbol, little, what do you call that symbol from 90 degrees between two? The right angle symbol?
Normal.
The normal symbol? I don't know. Okay. So, in any case, we've got that, and we're going to have a point right here. Let's see, what direction would it be oriented? It would be up like this. This would be dp. And this angle would be 90 degrees to the radial vector. So this is the small amount of magnetic field created by this small amount of current element. Okay? And you can use, see, this current element supposedly is coming out of the board. So you have to point your thumb out of the board using this version of the right-hand rule, and then the magnetic field it creates would be circulating around, and this would be a tangent to that circle at that particular point P on the x-axis. Does that make sense to you? To anybody, does it make sense? Ideally, it should make some kind of sense to somebody. Doesn't it? You get it? You get me? All right, so now we're going to use the law of Gauss R, and we're going to solve for the total magnetic field due to this whole ring of charge. But first of all, let me go ahead and write the equation for just this small elemental part of the magnetic field. Let's see, u sub 0 over 4pi times I ds crossed with r hat over r squared. Okay, well, if we want to get rid of the vector nature of this, we've got something nice we can do. ds and r hat are always 90 degrees to each other going to be the magnitude of little vector ds times the magnitude of the little vector r hat, which is 1, times the sine of the angle between. Sine of 90 degrees. Sine of 90 degrees is 1. Okay? So the magnitude of this is just going to be dB. And it's going to be equal to mu sub 0 I ds over 4 pi r squared. Good? Okay. Now r squared is what? R squared would be equal to a squared plus x squared. You agree with that? Okay. Now, if we go all the way around this, notice that everywhere you're going to have, you can break this down into a component this way. This would be dv and dx, and a component this way. We'll call this dv perpendicular to dx. Agree? Does that make sense? Yes, no, maybe? Okay. Well, if we go all the way around, which one of these components is going to cancel?
The r?
Which one? Yeah, dv perpendicular to x, right? This will add all the way around. This will eventually cancel. Agreed? Just from the symmetry of the problem, circular symmetry around the x-axis. Okay, so we really only need this component. Agreed? So we need to take this and multiply it by the cosine, whatever this angle is here. Well, this angle and this angle are the same. Would you agree with that? Does that look right to you? Do you agree that those two angles are identical? Okay. Does anybody need to see why? Okay. Well, if they are, then we need cosine of phi. And cosine of phi, well, what is it? It's the adjacent side over the hypotenuse, right? So that's going to be a over r, but r is equal to a squared plus x squared raised to the 1/2. Does that make sense? So dv in the x direction is equal to this times cosine. So it's going to be u sub 0 I a ds, all of that divided by 4 pi times the quantity a squared plus x squared raised to the 3 halves. And it does have a vector nature to it. It points in the x direction. So multiplied by 9. So this is the small amount of the magnetic field created by that small amount of the total current element oriented in the direction of interest, because anything else will cancel. So we can find the total magnetic field along the x-axis now. It's going to be equal to the integral of all these small parts of the magnetic field added together as we add using integration. And let's see, what can come out front? U sub 0, I, and a are all constants. They can come out front. 4 pi, a, and even x is a constant if we integrate with respect to the arc around the loop. So all of that can come out front. So we have u sub 0, I, a, divided by 4 pi times the quantity a squared plus x squared raised to the 3 halves integral ds. Oh, we've got 9 halves. Okay, well, if we integrate all the way around the arc of the ring, we just get start at 0 and go to 2 pi a. So just multiply by 2 pi a. And we'll have u sub 0 I a squared I hat all divided by 2 times quantity a squared plus x squared raised to the 3 halves. Is that right? That's right. Now, so this is the magnetic field due to a loop. Okay, along its axis. It's all that. Where x, the x axis is considered the axis of the loop, perpendicular to the plane. What if, so I'm going to write down u sub 0 I a squared divided by 2 a squared plus x squared raised to the 3 halves. Now let's do this. If x is much, much greater than a, then, and why would we want to consider great distances away from the radius, many, many times the radius of the loop? Well, because if we're talking about, say, the magnetic field due to an atom, then think about how small the radius of that loop is. Very, very small, half the diameter of an atom. So the magnetic fields that we're interested in are usually very far away from the atom itself. We were talking about macroscopic size, like if we're concerned with the magnetic field of a permanent magnet, say. Okay? So if we do that, if x is much, much greater than a, then this part right here, x squared, becomes much, much greater than a squared. A squared can basically be forgotten. And we end up with x squared raised to the 3 halves, which is what? It's x cubed, right? So b, along the loop axis, goes towards u sub 0 I a squared I hat divided by 2x cubed. Okay. Now, did I talk with y'all about the magnetic moment? With the magnetic moment, it was written as mu, and it's equal to I times A. So you're talking about a current flowing around a loop with an area A. Well, in this case, that would be I times pi A squared, right? So that's going to be pi times I A squared. Well, guess what? We've got an I and an A squared here. No. So we can write this if we want to as, let's see, u sub 0 mu times I hat divided by 2 pi x cubed. And this is the magnetic field along the axis of a loop if you're talking about for values of x much, much greater than a, where mu is the magnetic moment of the loop and x is your distance away from the plane of the loop. Now remember when we measured or tried to come up with an equation for the magnetic field due to a permanent magnet? What was the power that I was hoping that x would be raised to? Do you remember?
Should be around 3, right?
-3. Yeah. -3. Yeah, ideally, and this is pretty much true for all permanent magnets, the magnetic field dies off as the cube of the distance, okay? Which is what you should have measured when you did this lab. How many people got that? Something close to -3 power. Anybody else?
I got -2.9.
Yeah, perfect. Yeah. So close enough. Interesting. Okay, so yeah, that's why. Okay. Another way to look at it is this: the further you get away from the magnet, the less intense the pull of another magnet is, right? And it's a very intense thing if you get those magnets close to each other. The attraction goes up really, really fast. So they're very hard to work with when they're really close to each other. And it's because of this cube nature of the inverse cube nature of the force to the distance. And it works like that because you've always got a North Pole and a South Pole kind of counteracting each other with a dipole of any kind. And magnets are all dipoles. Okay, so that's, oh, can I see your book? Is that the way they did it there? Okay, where A is the radius of the loop. Oh, is that at the center? That's at the center of the loop. Okay. Yeah. Okay, so there we've got the inverse cube nature. Now let's take it the other direction. What if x is equal to 0? If x is equal to 0, you're right at the center of the loop, right? Agreed? So if x is equal to 0, this goes away. You've got a squared raised to the 3/2, which is a cubed on the bottom. But you've got an a squared on the top. So in the center of the loop, b at center of a loop will be equal to u sub 0 I divided by 2a. Yeah. And that will be the strongest, that'll be the place where the magnetic field is the strongest. And it'll die off as the cube of the distance in either direction. So it looks kind of like a bell curve, the strength of the magnetic field. The nice thing about this is that, and this is used in technology everywhere. If you want a given strength magnetic field, what do? Well, you make a loop of wire and you push a current through it. And you know the magnetic field at the center will be directly proportional to the current and inversely proportional to the diameter of the loop. So if you want a really strong magnetic field in a small region, all you got to do is put a loop of current with or put a loop of wire and push current through it. You'll have a strong magnetic field right in the center of that loop. Now, if you want to magnify the amount of magnetic field, instead of using one loop, use 1,000. And basically what you do is just multiply this by the number of turns. And if you look in your book, you'll see there's a capital N on the top of that equation that I did not include, where capital N corresponds with the number of turns of wire that they use. And they call that a coil, they call it a solenoid, they call it an inductor. All of those terms are used for loops of wire that have current flowing through them. Very important in electric magnetic technology. You remember doors that have, car doors that have a button? And remember when they used to have the lock where the stem would come up and you could push it down? these wires are separated by a distance d. Didn't we do something like this?
With place,
What is that?
say,
Okay. Well, tell me, if both of these wires have current flowing through them, let's say they're infinitely long, will they be attracted or repelled to each other, or will they exert any kind of force on each other? Well, if you use this version of the right-hand rule, okay, can you tell me the direction of the magnetic force or magnetic field acting at the location of wire number 2 due to wire number 1? What direction will the magnetic field be oriented at the location of wire number 2, this bottom wire, due to wire number 1?
when you try to push it into the board.
It will be into the board. Okay? Think about it. If your thumb points in the direction of current 1, then your finger is going to right hand naturally curl out of the board above wire 1 and into the board below wire 1. Agree? In the plane of the board. So I can draw that here. That will be V1. In other words, it's magnetic field due to wire number 1. Well, using this new magnetic field equation, mu sub 0 I1 over 2D. Isn't that the equation I've got? Oh, wait a minute, that's for the long straight wire. What's the magnetic field for a long straight wire? B1 is equal to, for B, for a straight mu sub 0 I divided by 2 pi r. Yeah. Good. Now what about the force? What about the force that is exerted on wire number 2 due to the magnetic field created by wire number 1? This version right here. Yeah. B points into the board. I to the right, so the force exerted is upward. So this is the force of 1 acting on 2. And it's equal to I2 L cross B1, where L is the length of the wire. Well, L cross B is just L times B times the sine of 90. Because B is in the board, L is in the direction of the current, which is 90 degrees to each other. So this is just I2 L B1. And here's B1. So the force of 1 acting on 2, wire 1 acting on wire 2, is going to be mu sub 0 I1 I2 times L divided by 2 pi d. Now we're going to divide through by L, and we'll get the force on 1 acting on 2 per unit length. L is equal to mu sub 0 I1 I2 divided by 2 pi. So the wires are attracting each other. Well, no, I haven't proven that yet. I've just proven that wire number 2 is being attracted upwards toward wire number 1. What is wire number 1 now? You have a force pulling it toward wire number 2, right? Does it? Well, what about the magnetic field created by wire number 2 at the location of wire number 1? What direction would that be oriented? Out of the board, right? We draw that here like this. So this is B2, 2, and it's equal to mu sub 0 I2 over 2 pi d. And then using this version of the right-hand rule again, now your thumb points in the direction of I1. Your index finger has to point out of the board now because the magnetic field to wire number 1 acting to wire number 2 pointing out of the board, so the force now is inverted down. So this will be the force of 1, wire number 1, acting on wire number 2. And that's going to be equal to I1 times L cross with V2. And if you go through the whole thing again, you get exactly the same equation, which you should, according to Newton's third law. Thing 1 pulls on thing 2, thing 2 pulls back equally on thing 1. Okay? So, two wires that carry current in the same direction attract each other. Okay? On the other hand, you can find out that if the current is anti-parallel, the currents are going opposite each other, then the two wires repel each other. We did talk about this before, didn't we? Didn't I tell you that's why high tension lines, high voltage lines hum? No. I've taught this class so many times that they all kind of run together. But y'all are my favorite class ever. So. It's true. Now, what was I going to say? Oh, have you ever climbed those high tension, high voltage towers? You've seen them off the highway. And when I was a kid, I thought that was a really good idea somehow. And it's not field trip. No, we're not. But yeah, so I would climb those things, and if you got up close to the wires, you can hear them hum. That's probably not good. Yeah. What's going on there? Why are they humming? Because of this. You think about it. If the currents, well, all the currents are Is that how you spell Amperian?
Your guess is.
Okay. Okay, so what ampere sound was this? Kind of like Gauss's law, but for magnetism. Okay. Now what the heck does that mean? Well, first of all, we found that wires that carry current produce a circulating magnetic field, right? Okay. So what Ampere wanted to do was find a way, if you knew the current, to find the magnetic field easily. Okay? And here's the way that works. If you took, okay, all of these wires create a magnetic field. If you make any shaped loop that completely encloses around itself, and that's why the circle on the integral sign has to be an enclosed loop. Okay, it comes back in on itself. Okay, if you take a line integral of the magnetic field all the way around that loop, so what are you doing? Breaking each piece of the loop into a tiny little section, multiplying its magnetic field there, times in the direction that the loop's going, times that little segment, that little length of that segment. And if you added all of that up all the way around, it would be equal to a constant u sub 0 times whatever current is enclosed by the loop. Okay? You believe me?
It's on the board.
It's on the board. It must be right. I wrote it down, so it must be true. So, yeah. That's, you know, let's try to forget. Okay. Now, here I'm going to have a current carrying wire. All right? And the reason why we're introducing this is to see we already have the ability to find the magnetic field due to a current carrying wire. We already did that using the law of Biot Savart, right? But Biot and Savart, what they were really trying to do is come up with this. Let me show you how much nicer this works. To use Ampere's law, you need to choose the right kind of loop. We could use a square if we wanted to around this, a closed loop around this current carrying wire to solve the magnetic field. But a square would still work, but it'd be a nightmare trying to deal with it mathematically. So what you want to do is choose a shape that everywhere the magnetic field will be constant due to this, and everywhere the magnetic field will be oriented in the same direction as your line of integration, as you're integrating around the line. Because if the magnetic field vector and the integration, the line of integration vector are pointing in the same direction, the dot product nature of this disappears, right? Because it's going to be the cosine of the angle between, which will always be 0, which is just going to be 1. Okay? Cosine of 0 is 1. So, if you choose your Amperian loop wisely, then this, which can be a very complicated integral to deal with, will become this, v times the integral dl. And v times the integral dl is just v times, how do you spell perimeter? Hold on, slow. P-E-R-I, meter. Okay, so P times the perimeter around your loop. Does that make sense? So, what do you think the best shape would be? It's just a line.
A circle.
A circle. So should it be a circle with this way out someplace close to the edge? Or do you want to put the circle with this right at the center of the circle?
I'll have that as the center.
I think you've chosen wisely. So let's say this is R. So this is our path of integration, P-O-I. And the magnetic field is everywhere the same value, because everywhere you're the same distance from the wire, and everywhere we know that it's oriented in the same direction as the path of integration. Agreed? Using this version of the right-hand rule. So we have integral dl is equal to mu sub 0 I, which is using this. So v times, what's the distance around this circle? About 2 pi r is equal to mu sub 0 I. Right? Divide through by 2 pi r, and you get the magnetic field field due to a long wire is equal to mu sub 0 I divided by 2 pi r. Well, that's simpler. Don't you agree? That's simpler to use the law of Beavis form. That makes sense? Okay, so there's an example of the use of Ampere's law. So what do you want to use Ampere's law for? If you have the current, you can use it to solve the magnetic field created by current. But you have to have the right shape Amperian loop, and it doesn't work with every type of current configuration. So so it's a little limited in the same way that Gauss's law was. You don't use it. It can work every time, but it doesn't make sense to use it sometimes because it's mathematically so difficult. But we found a nice, easy thing we can do with it. Now, okay, what's that?
Heater.
Spring. Okay. What's that? Yes, it's a coil, but it's cut cross-sectional. Okay. So let's do this. Let's say we've got a current flowing into this. Okay. So it's going to be flowing all the way around, right? And it's going to come out here. Make sense? Okay. So if it's going in, then it's coming out here. So it's a dot here, dot here, dot here, dot, 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 dot. And then it's flowing around and in here, and, right? So this is I of the plane of the board. Good? Make sense? Okay, so that makes sense?
Yeah.
Now my question to you is there a magnetic field in the region enclosed by these current carrying loops of the coil? Should be, right? We've already calculated the magnetic field at the center of current carrying loop. Here's a bunch of them. Okay. So I'm going to draw an Amperian loop here. Let's see. And let's say this is I'm going to solve. Can you tell me what direction the magnetic field would be oriented in this? Toward the left. Yeah, I would agree. If you're inside the enclosed region, enclosed by the coils, then yeah, I would say that the magnetic field would be oriented, right, this way, or yeah, that way. That makes sense? So we can draw it like this. And so this is going to become the North Pole. This will become the South Pole. This is the direction we had the current flowing. That makes sense? So you've got a very dispersed field lines on the outside, or very low density field lines on the outside. They're very constricted because they all come through the center, right? In the center, in the region enclosed by the current carrying coil, the magnetic field is very intense. This makes sense to you? Now what we want to do is solve for the magnetic field in this region. That's the working region of a coil. So what we want to do is use Ampere's law. Okay, we need to integrate, do a line integral all the way around this square, and set it equal to u sub 0 times whatever the enclosed current is. That's the instruction set that we have with Ampere's law. So this B dot dl. I'm going to start at A. I'm going to go this way. So I'll have the integral from A to B of B dot dl plus the integral from B to C of B dot dl plus the integral from C to D of B dot dl plus the integral from D back to A of B dot dl. Yes? You got a problem with that? Maybe tell me. Do any of these, do you understand how this one integral is comprised of these four? We've cut this into segments. Now, I've got a question. Did any of these cancel? Luckily, this one cancels. Why? A, B, and Y.
Because they're on
Perpendicular.
no, perpendicular.
Yeah, because the path of integration is perpendicular to the direction of the magnetic field. So the dot product tells us that we're going to have 0. Okay? We have the sign of 90, which is cosine. I'm sorry, dot product. Cosine of 90. I was thinking log units of r. That's a cross product. This is a dot product. So yeah. So it's going to be the magnitude of the magnetic field times the magnitude of the integration element length times the cosine of the angle between cosine of 90, which is 0. Okay, so this is 0. This part is also 0 for the same reason. Okay, so that leaves us with two parts. Now, which path, this path or this path, have the highest strength magnetic field? DA or BC? Which one has the highest strength magnetic field? This one. B to C, right? Inside the region enclosed by the current carrying coils. Out here, the magnetic field is so small that it's close to 0. So we can disregard So, this one is approximately equal to 0. So all we really need is this one, the integral of v dot dl from b to c. Okay. Well, it turns out that the magnetic field is fairly constant in this region, so E can be drawn outside, and the direction of the path of the magnetic field and the direction of the path of integration are identical. So we just get V times this length, which we'll call H. And that's it. So all of that reduces to V times H, and that's equal to mu sub 0 times I enclosed. Okay. If our current in to this coil is I, what is I enclosed? How much current is actually passing through the area enclosed by our Amperian loop? Any idea?
Can you repeat the question?
How much current is passing through the plane enclosed by the Amperian loop?
Would it be the current in times the number of loops in the
Yep. The number of loops enclosed times the current passing through each loop. So we have to worry about how many, coils are enclosed, right? So we're going to have V times H equal to mu sub 0 times N times I, where I is the amount of current flowing in to the loop, and N is the number of enclosed loops. So if we divide through by H, we get V is equal to mu sub 0 times big N times I over H. But little n is called the turn density. And little n is equal to the total number of turns divided by the length of the coil. Okay? So we can take this and plug it in here, and you get V for something called a solenoid. Is equal to mu sub 0 n times I. So a solenoid is a current carrying coil that is used to produce a given magnetic field. What do you need to have a strong magnetic field? You need a lot of turns per unit length. You need a lot of current flowing through each coil. That can produce a strong magnetic field. And you can design that magnetic field to be whatever value you want. So it's very, very useful and it's used in all kinds of